In your study of kinematics, you have learned how to deal with the displacement, velocity, and acceleration of a body in motion without considering the forces responsible for the motion. However, in kinetics, you are going to study the variables of a body in motion along with the forces that are responsible for the motion. Let us take the example of the start of a football match. The football would not move until a player kicks it. If you want to load a barrel onto a truck, will it go up just by itself because you want it to? No. You have to either lift it or roll it onto the truck. In each of these cases, the body was at rest until an external force was applied to move it. Similarly, when a barrel is being unloaded from a truck using an inclined plane, it tends to roll down fast unless its motion is restricted by some opposing force. In this case, the barrel has a tendency to move faster, but is being restricted by a force due to an external agency. In all these examples, the external agency applying the force was in contact with the object in motion. Hence, these forces are known as contact forces. When you drop a ball out of a window, it falls down. How did the ball go down when you did not apply any force on it? The agency applying the force is the earth, and the force is called gravitational force. This gravitational force is invisible and is a non-contact force. If you take a magnet near an iron nail placed on a table, the nail moves. Here again, there is an invisible force acting, which is magnetic force. Magnetic force is also a non-contact force. In all these examples, we saw that an external agency applies a force, either contact or non-contact, to accelerate a body, which is at rest, or to retard the motion of a body, which is in motion. Thus, we can say that a force applied by an external agency either accelerates or retards a body. Now consider a body moving with a constant velocity. Is there a need for an external agency to apply a force to maintain this motion? Yes. External force is required if the body is in our world, where frictional force acts on all the objects. However, in the absence of friction, like in space, no external force is required to maintain uniform motion in a straight line. To answer this question without any ambiguity, we first have to go into the history of kinetics and see what mistakes were committed before Newton's laws of motion were postulated. Aristotle put forward his view. An external force is required to keep a body in motion. This seems to be right when you apply it to all the day-to-day activities taking place around us. For example, to pull a toy, a boy applies a pulling force on the string attached to the toy. As soon as he drops the string, the toy stops. It seems as if what Aristotle said holds well in this example. However, If you carefully analyze the external forces acting on the toy, you will find that the pull exerted by the boy is actually equal to and opposite to the frictional force between the toy and the ground, which is again an external force. And hence, the net force acting on the toy is zero. We can thus conclude that the force applied by the boy is not in any way responsible for the motion of the toy car. In fact, the applied force just helps in overcoming the friction experienced by the toy. This is an example from our existing world. Now, let us go into a virtual world where there is no friction of any kind. Then the boy need not apply any force to keep the toy moving with uniform velocity. This is exactly what Galileo said. Galileo proved that no external force is required to move a body with uniform velocity in the absence of friction. Galileo conducted two simple experiments before postulating the law of inertia. The first experiment was with one inclined plane. A roller rolling down an inclined plane on its own accelerates. A roller rolling up an inclined plane on its own retards. A roller rolling on a horizontal plane neither accelerates nor retards, which means that the roller should move with constant velocity when there is no friction between the roller and the horizontal plane. The second experiment was with two inclined planes. When the slope of the two inclined planes is the same, a roller released from rest on one plane rolls down that plane and climbs up the other plane to the same height from which it was released, or a little less. When the slope of the second plane is reduced, the roller climbs up to the same height, but this time it travels a longer distance. When the slope of the second plane is made zero, that is, it becomes horizontal, the roller moves infinite distance. This can happen only in a situation where there is no friction. Actually, the roller comes to rest after moving some distance as frictional force acts opposing the motion. From these experiments, Galileo concluded that in either case, the state of rest and the state of uniform linear motion with constant velocity, the net force exerted on a body by the external agencies is zero. Therefore, to maintain uniform velocity, the external force required is only equal to but opposite to the frictional force, such that the net external force is zero. Let us put the same statement in other words. When the net external force applied on a body is zero, a body that is at rest remains at rest, and a body that is moving with uniform velocity in a straight line will continue to do so. The tendency of a body at rest to remain at rest, or of a body moving with uniform velocity in a straight line to stay in motion with the same uniform velocity, when the net external force is zero, is called inertia. In simple terms, inertia means resistance to change or resistance to acceleration. Newton's laws of motion have their roots in Galileo's law of inertia. In fact, Newton's first law of motion is almost the same as Galileo's law of inertia. Newton's first law of motion states that every object continues to be in its state of rest or of uniform motion in a straight line, unless compelled by some external force to act otherwise. If you observe, there is no mention of acceleration in Newton's first law of motion. This is because when a body is in a state of rest, it has no acceleration. Similarly, a body in uniform motion in a straight line does not accelerate. Based on these facts, we can express Newton's first law of motion in two more very useful forms. 1. If the net external force on a body is 0, its acceleration is 0 and vice versa. 2. A body accelerates only when a net external force acts on it. These two forms of the law are extensively used while solving problems in kinetics. Let us apply what you have learnt in this module so far to analyze some day-to-day events. When you are standing on firm horizontal ground, what are the external forces acting on you? What is the net external force acting on you? Let us try to answer the first question. The first thing that comes to mind is your own weight, say 500 Newton. This force acts vertically downwards. Is there any other external force acting on you? You can now apply the knowledge from this module to analyze these situations. You are at rest. That means your acceleration is 0. Since you have already identified one external force acting on you, that is, your weight acting vertically downwards, there must be at least one more force which is equal but opposite to your weight, so that the net external force acting on you is 0. This force is the normal reaction between your feet and the surface of the ground. While attempting to answer the first question, you have also answered the second question. The answer to the second question is net external force acting on you is 0. Let's consider another situation. What are the external forces acting on you if you are standing in quicksand instead of on firm ground? Your weight is the same. But what about the normal reaction? It can't be equal to 500 Newton. It is definitely less than 500 Newton. How did you come to this conclusion? Simple. You are sinking into the quicksand. That means you have an acceleration vertically downwards, which implies that there is a net external force acting vertically downward. Let's take an example from a physics laboratory. An iron cube is placed on a glass sheet, which is fixed to a wooden plank. This wooden plank is hinged to a horizontal surface. The wooden plank is slowly tilted until the iron cube is about to slide down on its own. That is, without any external force being applied to it. This position of the inclined plane is known as position at impending motion. Theta is the angle between the inclined plane and the horizontal surface. We now have to identify the external forces acting on the iron cube. W Newton is the weight of the iron cube acting vertically downward. On resolving this force, W, along with x and y directions, we get Wx is equal to W sine theta and Wy is equal to W cos theta. As W and theta are known to us, Wx and Wy can be calculated. At the point of impending motion, the iron cube has the tendency to slide down, but is prevented by the frictional force, F, between the glass surface and the surface of the iron cube. How do you find the magnitude of this frictional force, F? There is no motion of the iron cube in the x direction. That is, the iron cube is at rest as far as the x direction is concerned. This implies the net force in the x direction is 0. Net force along x is equal to F minus W sin theta is equal to 0. Therefore, F is equal to W sin theta. The iron cube is not going into the glass sheet, which implies that the iron cube is at rest as far as the y direction is concerned. Hence, the net force in the y direction should also be 0. N is the normal reaction of the glass sheet on the iron cube. We can now write net force is equal to N minus W cos theta, which is equal to 0, or N is equal to W cos theta. We have used Newton's first law of motion to find the value of F and N, which were not known to us.